In this video, we'll see conservation of momentum. Total momentum does not change during a collision. The total will not change. Just to remind ourselves, momentum unfortunately has a little p for its symbol. The unit of measure is the cumbersome kilogram meter per second. So we would say P equals 300 kilogram meters per second. And our formula is little p equals mv. I use this example of two balls colliding throughout. Before collision, there's a collision, and after collision. Let's see if this example here demonstrates conservation of momentum, where the total momentum does not change. See, this guy has 50 and this guy has 0, so the total is 50 kilogram meters per second before. I use this to say, wait a minute, the before and after are the same. Is it? Yes, it is the same. There's your conservation right there. No change in total momentum. And then these guys are 30 and 20, and they add up to your 50, don't they? So this is your classic example of conservation of momentum. Let's try this. Let's see if we have 70 here and 0. That means our total here on the left is 70. So what must be our total on the right? Yep, it must be 70. Conservation of momentum. Total does not change. We can work from right to left as well. Here we have 40 and 50. That adds to 90, correct? Which means by conservation of momentum, our momentum before the collision was 90. Conservation, the total does not change. Now let's try our first simple conservation of momentum problem. I want the momentum of y, ball y, after collision, right here. I want his momentum. Well, let's see. We have everything we need here. We have both of them. 50 plus 0 is 50. Which means that total number must be 50 afterward. That's your conservation. Now I know this one to be 10, so would you agree this one has to be 40? 50 minus 10 is 40, or these two add to 50. There you go. So we found this missing one. Starting from the right, we moved to the left and found that missing momentum. We can go the opposite direction too. Here where we have both of them are on the right-hand side. So this one becomes 40, doesn't it? And I can bring that forward here to 40 because of conservation of momentum. Now that's 30, so by subtraction, that minus that, this one is 10, isn't it? So we can go right to left or left to right, depending on one side you'll have all the numbers you need, one side you won't. All right, our third problem. Now, the difference here is so far I have given you these momentums. See, I've given these to you, but now I'm not going to do that. But I do give you enough to calculate them. I give you mass and velocity. And isn't that enough to calculate momentum here? Sure it is. Mass times velocity. 6 times 5, this one's 30. 6 times 0, that one's 0. Total is 30. Conservation momentum. Do I know enough to find one of them? Sure, I can find that one, can't I? 18. I want that momentum. I've got to subtract. 30 minus 18 is 12. Because 12 and 18 now will add to 30. We have our conservation of momentum. This is a similar problem, but we're going to work from right to left. Here I have all my information here. That's 18. That's 24. They add to 42. 42 comes over here, correct? Sure. This one's 30, right? 6 times 5. So this one has to be 12. Because 30 and 12 equals 42. Easy enough, right? Your video code is yes, yes. All right, here's our final problem. Let's see. I want to find that velocity. Let's look at this. I've already done most of the calculations. 42, 12, 54, 54, 36, 18. I've got all these. I got the momentums. Now the question is, what's that velocity? That's the last thing you got to know how to do. Well, let's see. For this one here, right here, don't I have P? I do. Do I have mass? I do. Can't I substitute and calculate V? Sure enough, 18 here equals 6 times V, and you'll find your V is 3. So at the end here, you can find the velocity or even the mass you need to by doing a little calculation. You know your momentum here, plug it in, find the one you're missing. That's it. That's all there is to conservation of momentum. Bye.